So I'll introduce Mike Cully-Sleight here. He's our BMS engineer, and he's going to do a little bit on the BMS systems that we've been working on.
Hello. So, first of all, a build management system can be split into three different sections. There's the field section, which encompasses the sensors, the actuators, pumps, and meters. And then there's the automation section, which is the brains of the BMS section. This is generally a BMS controller that holds the control strategy. And then there's the management system, which is generally a head end or a supervisor. And this gives you insight into the control system and is generally a graphical display of the mechanical layout with sensors and plant statuses throughout. So you may have a few control panels in a building. You would generally have a control panel for, say for example, in a energy centre, which would do all of the heating plant and has all of the field devices wired back to that control panel. On the fascia of that control panel, you have a hand-off and auto selector switch. That selector switch. The hand position means that it will ignore the BMS and just ask the plant to run. Off is off, and an auto will mean that the plant will run at the dictate of the BMS. Within the control panel, you have a BMS controller and hardwired relay logic. That hardwired relay logic ensures that the plant is run efficiently, or is run safely, regardless of whether the BMS controller has failed or whether the plant has been put into hand on the front of the control panel. For example, if a boiler primary pump run status has to be present for a boiler enablement to be allowed, because that is in relay logic. That's in both the hand and the auto position. And with controllers, you generally have inputs such as sensors and feedback from, say, a pump run status, and then you have outputs, which will either be the enablement of a piece of plant or an actuator position. There are two main types of plant controller, of controllers. One is main plant, which is freely programmable. This means that it is bespoke software. And this bespoke software is dependent on the inputs and the outputs. And that is different because every building is built differently, and every manufacturer will have different input and output requirements for the field devices. The other sort of controller you can have is a terminal controller, which you can have the option of fixed strategy. For example, this can be used in a fan coil unit because there's very little changes within the fan coil unit operation, and this can easily be adjusted via some basic settings for the specific fan coil unit. So within the controller, you have the control strategy. This replicates the relay logic with increased energy efficiency. It utilises optimized start and stop modules, as well as control loops or PID loops. The strategy can also be engineered to be a demand-driven approach, which ensures optimal energy efficiency. And then the head end or supervisor gives you insight into the control system. There's generally no control strategy. It's a graphical layout of the mechanical system with sensors, plant statuses, and end user adjustments. There are many communication protocols, and here's just an example of a few of them. Some of which are open source, such as BACnet, Modbus, and MQTT, and some of them are licensed. The term integration is given to control systems talking to each other. Some of which will be the most common way for integration to happen is via open source protocol, such as BACnet, Modbus, and MBus, or you can have a specific driver. A driver is a bit of software where one system would specifically need to talk to another system. For example, a Niagara device would have a trend driver to pull the information from the trend system. This one, I'm going to need my notes. In my experience, I found that there are barriers to energy efficiency within the BMS industry. Firstly, I will talk about new projects. Firstly, I will talk about new projects and how I found that the description of operations is often very vague and left to the BMS engineer to do their best. Or there are mechanical changes throughout the project and the description of operations does not reflect this. Like all industries, different BMS project engineers have different skill and knowledge levels. Not only this, but contracts can be limiting. The strategy could be written by one company, while the point-to-point and cause and effect commissioning is carried out by another company. This extra layer can cause contractual and accountability arguments. Also, speaking from my experience, the quality of acceptance testing, also known as witnessing, varies massively on each individual project. The main theme is whether the heating works, whether the supervisor graphics are looking at the correct point in the field, and if there's hot water at the tap. That there has been no energy efficiency consideration of the heat network with any witnessing that I or anyone I know has been a part of. Each of these examples mentioned mean that the end product's energy efficiency suffers. Personally, I've spent weeks firefighting brand new buildings that have been signed off and are not even operational, let alone efficient. In regard to legacy buildings, the challenge is to bring the heat networks up to standards in a building that has not seen any recent mechanical changes. The client often does not see the requirement or benefits to optimise. I often hear the phrase, "It's been running fine for years," and are often sceptical. Ultimately, it's all down to awareness, that there's nothing tangible that people can see to give them guidance on how efficient or inefficient their system is. So we unlock data from the BMS, we analyse that data, and pinpoint inefficiencies in the system, whether mechanical, BMS, or both. As this data is driven and we produce key performance indicators, also known as KPIs, this removes guesswork. Richard will go into some more detail on KPIs later. Both mechanical and BMS needs to be optimised in unison for peak efficiency, in which we have expertise in-house. Above all, we provide visibility and awareness of the energy efficiency of a system. That the use of KPIs create a tangible figure that can be compared against the optimal performance of similar buildings. This covers both new and legacy buildings for optimization and long-term management. During acceptance testing, these KPIs can ensure that the system is not just working, but is efficient. We use MQTT as it is a lightweight packet of information, which means less stress on the network. The information is outbound, so there's no need to punch any holes in the firewall. This information can be secured via TLS and certificates. MQTT is an open source protocol which protects the client. Anyone will have access to this data with the relevant credentials. You do not need specific licensed software to work with MQTT. Just to clarify, to enable a BMS to export or publish, MQTT may require specific licensed software. Once the data is in the MQTT protocol, that is when open source software can be used. The MQTT data is sent and held in the cloud and is called broker. You can have numerous subscribers to that broker, which means the work to unlock the data from the BMS and send the information to the cloud only needs to be carried out once. If the same data is required by another company, then they can subscribe to that broker with the relevant credentials. For example, meeting companies may already have an MQTT broker set up in the cloud with all the metered data for billing. Rather than spending days retrieving all the same information from the BMS and exporting or publishing this data again, you can subscribe to another broker via an MQTT bridge. This will require liaising with the other provider, but saves on engineering costs. So how do we export or publish BMS data to MQTT? Well, this is a system-by-system bespoke solution. The control systems vary in age and manufacturer. We utilize as much of the existing BMS as possible. And where required, we will use third-party controllers for integration. Prioritizing open source, we choose the most reliable and cost-effective solution. So what are our take-home messages? Mechanical and BMS work in tandem for true optimization. There's a lot of data in the BMS, which we have a cost-effective way to unlock that data. We use open source solutions as much as possible, and you own any data gathered. To increase the energy efficiency of a system means there will be a reduction in costs and carbon. Key performance indicators provide a tangible figure that is more easily understood and can be compared to optimal performance. This aids both acceptance testing and long-term management to ensure energy efficiency is optimized and maintained. Thank you for your time.